Okay, good day. So still under the topic, design of tension members, but this time, so we are to design a tension member with a welded connection. So let's have this example. I determine the allowable strength, that is the ASD, and the design tensile strength, that is for the LRFD of the angle shown. So we are to use A572 steel grade 50. So these are the properties of the angle to be used and how it is welded to our main plate. So let's say this is the main plate or the main member, and this is our tension member. The properties of this tension member, which is an angle, so that is 200 millimeters by 150 by 19 mm. Then its welded length is equal to 150 millimeters. So this will be our L. So we are to consider the longitudinal welds, since if this is the direction of the force, again this is a tension member. So let's say PA or PU. So the welded connection L 150 millimeters is parallel to the direction of the applied force, or to the let's say the PA or the PU. Okay, so let's have the properties of the steel to be used. Let's say the properties of A572 steel, grade 50. So here in the Philippines, so we are using megapascals, so that's why so we are to convert 1 KSI is equal to 6.895 megapascals. Then for easier computation, we round it to the nearest whole number. If we are to search for the property of A572 steel, we have it as Fy, or the Fy, is equal to 50 KSI. That's 50 kips per square inch. So if we are to multiply this one to 6.895, that will be 50 multiplied by 6.895 megapascals. So 344.75. This is 344.75 megapascals. Let's say we are using 345 megapascals. Then the value of Fu is equal to that is 65 kips per square inch, and that is equal to we have 65 multiplied by 6.895. That's 448.175. So 448.175 megapascals. Okay, let's say the nearest whole number is 448 megapascals. Okay, so these are the properties of the A572 steel grade 50. Now, let's have our analysis. So for our analysis, the first one is for the GSY, or the gross section yielding. So for the gross section yielding, we need the value of the gross area of our section. So let's have the total area of this angle. So again, I can extend this dimension. Let's say this dimension will be, I'll be just dividing the angle into two rectangles. So this one will be 200 by 19 millimeters. Then what is 150 minus or less 19? So if this is 19 mm, so 150 less 19 is 131. So 131 by 19. So we just divide our angle into two rectangles. So what are those areas? We have two rectangles. That's 200 multiplied by 19 mm plus 131 millimeters multiplied by 19. And the gross area will be equal to 200 plus 131 multiplied by 19. That is 6,289. We have 6,289 square millimeters. Okay, so we proceed to the gross section yielding. So we have the nominal strength is equal to Fy multiplied by the area gross. So what is our Fy? 345 megapascals or newtons per square millimeters. Our area gross is 6,289 square millimeters. So we can cancel this mm. As you can see, the remaining unit will be in terms of newtons. So we are to multiply 1 kilonewton is to 1,000 newtons. For our answer to be in kilonewtons. So we have P sub n. The nominal strength will now be equal to, that's 6,289. Multiplied by Fy 345, then to be divided by 1,000 to be in kilonewtons. So 2,169.705. 269.705 kilonewtons. Now we are to consider what are the allowable and the design tensile strength. So that is for the let's say LRFD. Under GSY, we have a reduction factor P is equal to 0.90. So we have the ultimate load P sub U is equal to P multiplied by the P sub N. So let's have its value. We have P sub U is now equal to P 0.90 multiplied by 2,169.705 kilonewtons. So the design tensile strength under LRFD, this value multiplied by 0.9. So that will be 1,952.73. 1952.73 kilonewtons. Okay. So that will be under LRFD. Then if we are to proceed to the ASD, so under ASD we have that as our the factor of safety under GSY, or the gross section yielding, is 1.67. So we'll be having the allowable load will be equal to the nominal load divided by the factor of safety. So you have the P sub A is to 169.705 to be divided by 1.67. So allowable load under ASD to be divided by 0.9. That's 2,169.705 divided by 1.67. So 1,299.22. So 1,299.22 kilonewtons. So we have the design strength under LRFD, and we have the allowable strength under ASD. So that is under the gross section yielding. So let's have the allowable and the design tensile strength under the next consideration, the next analysis. That is the tensile rupture strength. So again, that is the first one, that is under the gross section yielding. For the second one, this is for the tensile rupture strength. So for the tensile rupture strength, supposedly we need the value of the net area. But for this case, the net area is basically equal to the gross area for a reason that, again, this is a welded connection. So for our welded connection, we don't have holes for bolts. So let's say this is without holes. Since we don't have holes for bolts, the area net is basically equal to the area gross. So how do we compute for the nominal capacity under the tensile rupture strength? P sub n is equal to the Fu multiplied by the effective area. So we have the area effective is equal to, or the net effective area is equal to the A sub n multiplied by the shear lag factor. Okay, so let's have the value of the shear lag factor. So so for this time, as if you are to observe our tension member, so the only welded member is the 200 millimeters, or the only welded leg is the 200 mm, and the 150 mm is free. So this will fall to case number 2. Okay, so case number 2, we have it in our table, this figure. Okay, so one member is welded to the main plate. For number 2, all tension members except HSS, or that is the high-speed steel, I think, a type of alloy, where the tension load is transmitted to some but not all cross-sectional elements by fasteners or by longitudinal welds in combination with transverse welds. So basically, the value of U will be computed using this equation. So we have the shear lag factor is equal to 1 minus the bar X divided by L. So we have L as the length of the welded length of the tension member. That is equal to, that is given 150 millimeters. All we have to do now is locate the centroid of this area. Alright, so let's say the centroid will be at this point. Alright, so we need this distance. So let's say this is the bar X. Okay, how do we locate this bar X? So we are to use Varignon's theorem. So I'll be just dividing again our area, or this angle, into two rectangles. So let's say if this is 150 millimeters, the thickness is 19 mm, the length is 150. The length is 150 millimeters. So we may cut this one, 200 millimeters. What is 200 minus 19? So this is one of our rectangle. Okay, then the other rectangle is this one. So that is 200 millimeters minus 19 mm. This will be obviously 100. 200 minus 19 is 180. It is 181 mm. Okay, then also 19 millimeters thick. Then how far is the centroid of this angle from this main plate? That is the bar X. So all we have to do is use the concept of Varignon's theorem. So that is, let's say the area total. We have area total times the bar X is equal to area 1 X of 1 plus area 2 X of 2. So a while ago, what is our total area? That's the gross area. 6,289. So our gross area is 6,289 millimeters multiplied by bar X. So let's say this green rectangle will be our area 1. That is 181 multiplied by 19. Its centroid towards the main plate is 19 millimeters divided by 2. Okay, then plus the other rectangle, let's say this is the red rectangle, will be our area 2. That is 150 millimeters multiplied by 19. And its centroid will be at a distance half of 150. What is half of 150 towards the main plate? That is 150 divided by 2, or 75. So if we are to solve for that value, 181 multiplied by 19 times 19 over 2 plus 150 multiplied by 19, then multiplied by 150 over 2, or 75. Okay, then this value to be divided by the total area, 6,289. That is 39.18. Let's say the value of bar x is equal to 30, again, 39.18 millimeters. Okay, so we have now the value of the bar x. So again, this type of connection for the shear lag factor will fall on case number 2. So that is, okay, we have U is equal to 1 minus the bar x divided by L. And again, it is a given that the connected length or the welded length of the tension member is 150 millimeters. Okay, so we are now to compute for that value. Okay, the shear lag factor is equal to 1 minus x or bar x divided by L is equal to 1 minus 39.18 divided by 150. So shear lag factor for this one will be equal to, yes, I think that's 39.18. Alright, it's 1 minus 39.18 millimeters, okay, to be divided by 150 mm. It's 0.738, or let's say 0.74. So we'll be having our net effective area for tensile rupture strength is equal to the area N, or basically equal to the area gross, since we don't have holes. That is equal to 6,289 multiplied by 0.74. So we have the effective area will now be equal to, let's say, 0.74 multiplied by 6,289. It's 4,653.86. So 4653.86 square millimeters. Okay, so we have now the area effective. Okay, we can now compute for the nominal strength for tensile rupture strength. So we have the P sub N is Fu. Okay, a while ago, the value of Fu is equal to, is 448 megapascals. So 448 megapascals, or the newtons per square millimeter, multiplied by 4653.86 square mm. Okay, again, to be divided by 1,000 newtons for our answer to be in 1 kilonewton, or in kilonewtons. Okay, nominal strength is now equal to, this value to be multiplied by 448, then to be divided by 1,000. That is 2,084. Okay, 2,084.93. So this is 2,084.93 kilonewtons. Okay, 93 kilonewtons. Okay, then we are to consider, okay, design tensile strength and the allowable strength. So for the LRFD, so reduction factor for tensile rupture strength is, that is 0.75. We have a P sub U is equal to the P, or that is P multiplied by P sub N. So our P sub U is equal to 0.75 to be multiplied by 2,084.93. So PU is now equal to, this is 2,084.93 multiplied by 0.75. So 1,563. 1,563.697, let's say 70 kilonewtons. So the ultimate strength for TRS, or yes, the design tensile strength. Then for under ASD, our factor of safety under TRS is equal to 2.0. So do you have the allowable load will be equal to the P sub N divided by the factor of safety. So P sub A is equal to 2084.93 divided by 2. So allowable load will now be equal to, we have that as 2084.93 divided by 2. So that is 1042.465. 1042.640 465 kilonewtons. Again, that is 1042.465. So these are the design strength and the allowable strength under TRS. Then if you are to compare as early as now to the values under GSY or the gross section yielding, we can tell that the values under TRS are safer, or they are the design values compared to GSY. If we are just to compare these two. Okay, then we proceed to the third analysis, third consideration, that is for the block shear. Okay, but before we proceed to the block shear strength, let us first clarify that the analysis, the gross section yielding, the same with the tensile rupture strength, that our assumption is that the failure will occur in our tension member, or that is on the given angle. Okay, so reminder, for our analysis under GSY and TRS, the failure will occur on our tension member, that is on the angle bar, on this given angle bar. So if we are now proceed on block shear strength, let's say this is our third analysis, the block shear strength. Okay, so we have the provision. So the AISC specification states that the available strength Rn for block shear rupture design strength is as follows. So nominal strength Rn is equal to 0.6 of FU ANV plus U sub BS FU ANT should be less than or equal to 0.6 of FY area gross V, then plus U sub BS FU ANT. So design strength again for ASD, so the same with the TRS, the tensile rupture strength, 2.0, and P is equal to 0.75 for LRFD. But again, if we are to do the analysis of block shear, our consideration should be the failure will occur in our main plate. So consider the main plate being ruptured. So from these equations, let us first clarify what is AN sub B or the A sub NB and the A sub NT. So A sub NB, these are the areas that will resist shear. So this area, again, the welded length a while ago is equal to 150 millimeters. And the welded length of the angle is equal to 200 mm. And the thickness of our plate, or the thickness of our main plate, is also equal to 19 millimeters. Okay, so that these properties are already given at the start of our lecture. So our main plate is also 19 millimeters. Okay, so again, if you are to consider this third analysis for the block shear strength, failure will occur in our main plate. So this again, this area is our A sub NB. That is the area of this main plate that will resist shear. So we have 2. Okay? So this is AN sub B, AN sub B. A sub NB, sorry. So let us compute for that value, the value of AN sub B. So we have the A sub NB is equal to, again, the welded length is 150 millimeters. That's 150 multiplied by its thickness, 19 mm. Again, we have 2. So we have here on the top A sub NB and A sub NB. So multiplied by 2. So that will be equal to, we have 150 multiplied by 19, then multiplied by 2. So we have that as 5,700 square millimeters. That is the cross-sectional area of the main plate that will resist shear, basically. Shear force. Okay, what about the other area? So we are done with the A sub NB. So this time, we proceed to the area A sub N T. So that is the net area for tension. So if this are for shear, the area for tension, the net area for tension is this portion. Okay, that is the welded leg of the angle bar. So it has a length of 200 millimeters. From our previous figure, that is the 200 mm. So let us compute for the net area of that section. So this is the A sub NT is now equal to 200 millimeters. That is the longer leg of the angle bar connected to this or welded to this main plate. Then to be multiplied by the thickness of the main plate, which is also 19 millimeters, and that is equal to, we have 200 multiplied by 19 mm is 3,800 square millimeters. This is 3,800 square mm. So let us now compute what will be the block shear strength, that is the Rn. So let's have this equation. That is the R sub N is equal to 0.60 of Fu multiplied by the A sub NB plus U sub Bs multiplied by Fu multiplied by A sub NT, or the area for net the net area for tension. So how do we what is the value by the way, what is the value of this U sub Bs? So for U sub Bs, by provision, U sub Bs, that is the tensile rupture strength reduction factor. Okay, so Bs stands for the block shear. The value is equal to 1 when tensile stress is uniform, such as in all tensile members and gasset plates and single row beams and connection. 0.5 when tensile stress is not uniform, such that as for multiple row beam and connections. But for the main plate, class, it is a single plate. So if it is acted, for example, for this portion, if it is acted by a tensile force, the P sub N or the R sub N, so we can assume that the stress will be uniformly distributed. Okay? So the tensile stress will be uniformly distributed since this is a single member plate. So we can use the value of U sub Bs equal to 1.0. Considering the value of the U sub Bs equal to 1.0. So let us now substitute. So we have, this is the Rn, or the R sub N is equal to 0.60. Our F sub U a while ago is 448 megapascals. A sub NB is, okay, that is 5,700 square millimeters. 5,700 square millimeters. Then plus, UBS is 1.0 multiplied by FU, that is 448 megapascals multiplied by A sub NT, that is 3,800 square millimeters. So we just follow this equation first. Okay. Okay, this one. So also available, I think, okay, for under AISC. So let's have this value. So R sub n is now equal to, by the way, this value will be under, will be in newtons, so divided by 1,000 newtons for all terms. So that this value will be in kilo newtons. We have the nominal rupture strength is now equal to 0.6 of 448 divided by 5,700 plus 1 by 448 multiplied by 3,800. And this is to be divided by 1,000 to be in kilonewtons. 3234.56 kilonewtons. But this value should be less than equal to 0.6. Again, from that equation, 0.6 of AYGB, 0.60 of AYGB plus UBS FU NT, ANT. So we have UBS FU multiplied by ANT. Class, for this problem, again, the value of ANB and ANT, since we don't have holes, okay? So we have the value of AGB the same as ANB. The value of AGT is the same as ANT. Net will be equal to gross. Again, so this is a welded connection with no holes. So we don't have holes for a bolt, since again this is a welded connection. So let us compare this value. This will be 0.60 of supposedly that is FY. That is 0.60 of FY AGB. FY a while ago is 345 megapascals. AGB is the same as the ANB. The 5,700 square millimeters. Plus UBS 1.0 FU 448 then multiplied by 3,800. Or maybe we can just say that we copy this second term. Okay. So let us have this is the computed R sub n a while ago, 3234.56 kilonewtons. Is it less than or equal to this value? We have 0.6 of FY 345. ANT is the same as ANV 5,700. Plus 1.0 multiplied by 448, then multiplied by 3,800. To be divided by 1,000. Again, we are dividing this term by 1,000 so that the value will be in kilonewtons. Is 2,882.3 kilonewtons. So 2,882.3 kilonewtons. So based on the condition, the value of R sub n should be less than or equal to 0.60 of FY AGB plus UBS FU ANT. So therefore, we are to use the value of R sub n to be this value. This value will govern 2,000, 2,882.3 kilonewtons. Then let's have our reduction factor and the factor of safety. So for ASD, 2.0. For LRFD, 0.75. The same as the TRS. Okay, for under LRFD, okay, we have the reduction factor. Okay, that is equal to 0.75. So we have that is RU, or RU, or let's say PU, will be equal to the same as the P of Rn. So we have the P of Rn is equal to, that is 0.75 of 2,882.3. So we have that as 2,161.725 kilonewtons. So this value will be under LRFD as the rupture strength for block shear. Then for and then we have ASD. We have the factor of safety is equal to 2.0. So let's say this is the R sub n divided by the omega, or the factor of safety. That is 2,882.3 kilonewtons divided by 2. So you have that as the R sub n divided by omega is now equal to, we have 2882.3 divided by 2. That is equal to 1,441. 1,441.15 kilonewtons. So these are the values under the block shear strength. So if we are now to go with our conclusion, so what is the least value? The least value among the three analysis, that will be our design values. Then if we are to compare, this is our final answer. Okay, so comparing the three analyses, so our design values will be for PU, that is equal to 1,563.70 kilonewtons. This is for LRFD. Okay, if you are to compare the value of LRFD values for the three analyses, so we have 1952 is greater than 15. 2,161.725 is greater than 15. So the safest value is 1,563.70 kilonewtons. That is the design strength. For the allowable strength, that will be equal to 1,042.465 kilonewtons. This is for the ASD. If you are to compare the allowable values per analysis, 1299 is greater than 1042. 144, I think it is 1441.15. Is that the correct value? Yeah, 1441.15 kilonewtons is greater than 1042.465. So, the analysis that will govern will be under the tensile rupture strength. So, these are the design values. Again, if we are designing load, or the safe value of the load, so the lower the value, the better. But if we are designing a dimension, the greater the dimension or the larger the dimension, the better. But you need to consider if this is an economical dimension. This will be our complete analysis for the given angle.